Awesome. So first of all, welcome everybody to back to our RealML reading group. We're very excited today to have Aldo Pacchiano, who's a postdoctoral researcher at Microsoft Research New York City. Aldo received his PhD at UC Berkeley, where he was advised by Peter Bartlett and Michael Jordan. And his research is in the area of reinforcement learning, online learning, bandits, and algorithmic fairness. Aldo, thank you so much for speaking today, and please take it away.
Thank you. Yeah, thanks for the invitation. So today I'll talk about two works. Mostly I'll focus on the first one. And this is a paper that appeared at NeurIPS 2021 and joint work with fantastic authors, Niladri, who is actually at Stanford, and Peter and Mike. So the title of the paper is On the Theory of Reinforcement Learning with once per episode feedback. It should said once, I think. So yeah, so these are the photos of the authors. So I guess, like, I don't know how exactly you run this thing, but feel free to ask questions, at least from my side, and we can make it a little bit interactive and so on. So this was a couple of years ago that we were thinking about reinforcement learning and what are the requirements of feedback in reinforcement learning. So the usual assumptions are that when you're taking actions in the world and observing states, you get to see a reward that corresponds to a function, perhaps, or that depends only on the state and action that you are taking. But thinking of some application domains, and even also from a theoretical perspective, poking at the limits of the model of reinforcement learning, there may be scenarios where per state rewards are not available. And these are things like when, instead of having access to a per state signal, we may have instead ways of evaluating whole trajectories of the systems or the agent's behavior. So as an example here, I have, so let's say you want to train a system or a robotic system to dance beautifully. So now when you define this kind of objective function, and you see perhaps a trajectory of the robot dancing, evaluating if it did it so in a beautiful way or not is not something that may be easy to evaluate in a Markovian sense or at a per state action kind of way. It's something that may depend on how the whole sequence of actions and states that the robot found itself at looked like to a human onlooker, but at sort of a global level. So in that setting, you don't have an easy, at least to define, a reward per state or per state action pair, but you do have perhaps a way of evaluating the whole behavior of the system or the agent in a whole trajectory sort of way. Similar things perhaps could be argued for things like self-driving cars, where if you want to make the car drive properly, it may be a little bit hard to define it at a per state way, but it may be easier to say that, yeah, the car drove well by observing its whole behavior along a particular predetermined trajectory, let's say. So sorry for this. Let me try to get rid of the sounds. Yeah, so what are the sort of requirements that we have here in, sorry, let me go back a little bit. So what are kind of the requirements if we want to model this mathematically? Well, the first thing is that to capture this kind of human labeling situation that I described, for example, for the dancing robot, you need to define a non-Markovian kind of reward signal that takes the whole trajectory and outputs a value. And this is, of course, like because in the presence of human supervision, per state rewards may be unavailable. So we're not the first people to think about how to do reinforcement learning with trajectory level rewards. There's previous work on that. So for example, the one at the bottom. So this paper by Jonathan, a friend who's a good friend actually, they introduced a model of trajectory level feedback, but in the form of a sum of per state rewards. So in our work here, we depart a little bit from this idea of a sum of per state rewards to instead think of evaluations of whole trajectories in a way that ideally mimics what a human labeler may do. So we try to come up also with plausible forms of modeling human feedback at the trajectory level. And we try to then come up with good algorithms or tractable algorithms in a theoretical sense for these kind of forms of feedback. So there's also some other works that predated ours that think also of alternative forms of feedback, but some of these ones are not thinking about evaluating whole trajectories at once. Okay, let me show you just what is the setup and the assumptions that we make. So we deal with episodic MDPs. This is a tuple that is made of, so an MDP, we're going to think of it as a tuple made of a set of states, set of actions, a transition dynamics, probability matrix, and a horizon that is of size h. Okay, so I'll also use this notation a lot throughout the talk. So I'll call tau a trajectory. So a trajectory is just sequence of state, action, and rewards, but in this case, there are no rewards for state action pairs. But it's just a sequence of state actions of size h. Well, 2h because there are 2 in each time step. And this symbol here will correspond to the space of all such sequences, this gamma here. So now what we're going to assume is that there is an embedding of the trajectories into a d-dimensional space that is known to the user that equals this phi of tau quantity. Okay, so then the trajectory reward model that we introduce works as follows. So let me actually just introduce it in this slide instead. So the idea is as follows. So every trajectory is then labeled as good or bad by, let's say, a human labeler. And what we're going to assume is that the probability of a label being 1 or good for a given trajectory follows this model, which is this logistic or this link function here, evaluated as this is a probability. It's a number between 0 and 1. This link function here evaluated the linear the dot product between this unknown reward vector W star and the trajectory embedding. Now I want to sort of comment that so this is a little bit clearer. So I'll use the notation y of tau to refer to a label, which is a random variable of trajectory tau, whose conditional distribution is this Bernoulli random variable that is defined by this model. Now this is sort of a plausible model for what human preferences may be, that captures things like separation between, for example, expected utility versus reward, in the sense that so this function shows a marginal the slope is such that when you move up in the value of this, I forget exactly how it's called in my head right now, the marginal increment in your utility here is smaller than the linear one that happens inside. Yeah. Okay. So that's also why this is a good plausible model for utility instead of reward. So perhaps a way to also think about this model is that instead of maximizing what would be a reward, which is in a sense is what this dot product here, what we're trying to optimize here is a utility, an expected utility instead. And the interesting thing that happens when you try to maximize for this simple preference model is that now the optimal policy has become non-Markovian because the problem has become non-Markovian. So adding this nonlinearity to this simple linear reward has made the problem much more difficult than it would otherwise be. So even in the setting where these phi maps correspond to a sum over features per state action pairs, when you add this nonlinearity here, the reward has become a non-Markovian function of the whole trajectory, and therefore the problem of optimizing for that reward is also non-Markovian, which means specifically that the optimal policies are now history dependent. So remember that in the usual reinforcement learning setting, the optimal policy only depends on the current state. But by adding this simple reward model, now the optimal policy does not depend only on the current state, it will depend on the history of states that have been visited so far. So let's, when I mention optimal policy and so on, I'm actually, without saying it, also talking about value functions. So let's define what that means here. So in this setting, we have that for any particular policy, if you start at state S, the following expectation is the value function of this policy, which now, instead of being a sum over rewards that you collect as state action pairs, it will be just this expectation over mu of the score of trajectories. And so if we have a particular given policy and the initial state is sampled from a state distribution rho, then the value function, or the value actually of that policy, is just this expectation. So our objective is to find a policy that maximizes this quantity. So the pi star policy that we want to find, ideally, would be one that maximizes over all pi's this v pi quantity. Now, so for our guarantees, our theoretical guarantees, we'll use the following quantity, which is called regret. So this is a measure of suboptimality, and you want to make your algorithm be able to minimize this quantity. And in this case, it's just the difference between the value of the optimal policy minus the values of the policies that we will be playing as we interact with the system. So just as a summary of results, and again, I'll mention again, the main challenge here is that when you assume a model of reward like this, the problem, even if it's tabular, which is the assumption we're going to make, has become non-Markovian, which means that you have history-dependent policies, which is different from the usual Markovian reinforcement learning setup, and that's the main challenge here. So we introduce an algorithm that is called UCVBI with trajectory labels. This is a modification of the traditional UCVBI algorithm for reinforcement learning in tabular domains. And we will show that this algorithm satisfies a regret guarantee that scales polynomially with the problem parameters, so the size of the horizon, the state space, the action space, and the dimensionality of the feature maps. There is a factor there that I'm not showing you that depends on the norms of the W star and the phi vectors, but we'll talk about that a little bit later. So the main takeaway is that even though the problem has become non-Markovian, because of the sort of low dimensionality of this kind of reward family, it's still possible to solve it in polynomial time. Okay. So any questions on the setup? Maybe I took too long for the setup, but
Hey, Aldo, I have a quick question. Sorry, I joined a bit late.
Yeah.
So pretty much you get to observe the reward only after the episode ends, right?
Yes, exactly.
Okay. And so this horizon age, so pretty much it does not play any role in the protocol, right? Except later on, probably in theory, you would sort of depend on it, right?
Right. Well, I guess it depends in that you have to wait 8 steps of running your policy.
Sure.
And it shows up in the analysis because you have to estimate the model, right? So that's where it's showing up.
Yes. Okay. Sounds good.
Yeah. Also, like maybe I don't know if people had this question, but this is often a question I get. When I describe this setup, is like, oh, why can't you just sort of add like a state at the end or something where reaching that state corresponds to a reward of 1 and not reaching a reward of 0? Well, the answer is that it's just not that simple, because this depends on the whole state of the trajectory. So the whole how the trajectory looks. So it's not really as simple as, you cannot make it Markovian that simple. We'll see later on that under some assumption on the phi's, when they are some decomposable, something roughly like what I just described, adding kind of like a state at the end, kind of works. But what actually works there is to add an extra component to the existing states to make this problem, that basically in that setting becomes a POMDP problem, into an MDP. But we'll talk about that later. So basically the point is like, easy fixes like adding kind of like a state at the end is not really going to make the problem now Markovian and then easy. You need to deal with the non-Markovianity, I guess, like head on.
And phi is given to you, right? So that's the input to the problem.
Phi, right.
Okay, and are there any assumptions on the dynamics, on the transition dynamics, or like Bellman operator?
Yeah, so right now we're just assuming it's
okay.
I mean, it's a tabular problem, what we're going to
okay.
be doing. I think other people may have already extended these things to like linear MDPs or other function approximation settings. So, but yeah, this is already like a couple of years old. So okay, so what are the assumptions? We're going to assume that the reward parameter, of course, we don't know the reward parameter, but is less than, has a L2 norm, less than some quantity. I think we does 1 if you want. And also the feature maps are bounded. We know the feature maps, like we know those features. So this quantity, kappa, plays an important role in the bounds. So why this is because, so if this signal, for example, the norm of y star is very, very large, then the mu function evaluated on some trajectories perhaps could be really picky. So it could be that the mu function only picks up, for example, a single trajectory as like a 1 and every other trajectory as a 0. So that is going to make the problem very hard. So this kappa quantity controls how picky in a sense, or how picky the landscape of 0, 1 or mu values is across trajectories. And if it is very picky, or you have the norm of W, or the quantities W transpose phi's are very large, either in a positive or negative direction, the problem becomes harder. So this is modulated by the norm of W. And this, of course, this quantity appears in the bounds and depends exponentially on the norm of B, on the norm of W. So, for example, in the case the norm of W is 1, then you have mu values that are roughly between, let's say, half to something small, right? So either so they don't go too much into like hard 1 or hard 0, and those are harder to learn from. So yeah, but in all of these, like, let's just think of B as basically like a constant for all of our bounds. So we won't delve too much into this specific part of the complexity, but it exists there, right? So that's why if you have a preference model that's very picky, that values some trajectories as 1 and some trajectories as 0, but without randomness, the problem becomes much harder. Okay, so the algorithm relies on the following procedure, which is to estimate W star. So how do we do this? Is given a couple of trajectories and their labels, we can use cross entropy loss, minimize the cross entropy loss to find an estimator of W star. Now, this data that was produced was not IID, right? So because it was produced by running different policies that could be changing across time. So that's one challenge. I mean, this is common challenge in online learning. I just want to comment that this, of course, this function is convex in this sort of linear setting, so you can minimize this easily. So what we can do is we can then get maximal likelihood estimator for W star, this W hat quantity, by minimizing the cross entropy loss. And we'll make use of this design matrix, which is just the covariance of the features of the trajectories we have seen so far in our bounds. Like it'll appear in our bounds. So what kind of bound can we get? We can get the following confidence interval bound for this W hat quantity. So we can show first, and this is something that exists in the literature. This came from some different paper, but this is a very common type of bound that you find, which is that the W hat quantities that we are producing by doing the MLE estimator estimate well the outputs of the optimal model, the true model, up to an error that corresponds to the inverse norm. So the current feature, the feature of the trajectory you're evaluating here, evaluate at the inverse norm of the covariance that has been collected so far. Okay, this is the usual. If you have seen linear bandits proofs, for example, it's sort of the same thing, except that now we have this mu quantity. And really how you can prove this is that this mu is Lipschitz. So actually this difference is upper bounded by some Lipschitz constant times the linear error. And that linear error that can then be upper bounded by something like this, roughly speaking. So why intuitively this is true. Okay, so this just holds for with hyperability, and this is going to be useful in the way in which we prove our bounds. So how does the algorithm work? As you would expect, so we initialize a model in some kind of arbitrary way. Some empty model, compute the MLE for finding the reward model. So this is a step that, taking the data you have collected so far, tries to learn a reward model. Then you compute an optimistic trajectory reward for all trajectories, basically, and use that. So this is the optimistic function for the reward of a trajectory. So given a particular trajectory, tau, and the current W hat model, so the MLE model, you can estimate a mu quantity that I think I'll describe in a second. Sorry. Where do you go? Yeah, you can compute a function that always overestimates the value of mu of W star comma tau using the confidence interval given by the previous slide. So that's what you will do, and of course this also depends on this needs to be using the empirical model, which is of course not the correct model yet. So all of these problems, I guess, or inaccuracies have to be taken into account to make sure that you're doing something useful here. Okay. So now also remember that the optimal policy class now is actually some history-dependent policy class. So that we have to deal with. And of course, then once you get this thing, you then just execute this policy and update the model. Okay, so main difficult thing here is to also talk about this policy class is history-dependent, so it's not Markovian, and this may cause issues. So let's just remember that. So let's deal with that now. Just kind of as a little reminder, the number of, in a tabular environment, so where you have state action pairs, the number of trajectory-dependent policies is really large. So in fact, it will scale something like A, the size of the action space, to the S times A to the H. So, basically something super exponential. Okay. So in contrast, when the size of the policy space for history-dependent policies, for Markovian policies, scales only as A to the S. Okay, why this is important is because all the guarantees will depend logarithmically in the size of the policy class that you are dealing with. Now, so if we are naive and we try to just use this set of all possible history-dependent policies, then what's going to happen is that our bounds will have the super exponential dependence on S times A. So that's not something you can do. Okay. So what comes to save the day in this setting is that for the set of problems that we are studying here, the set of potential optimal policies is actually much smaller. So think of it as if I have for any triplet that corresponds to an initial state distribution, dynamics, and a reward model, there is an optimal policy in this set that I can produce, right? So now roughly what's going to happen is that the set of these optimal policies given by these triplets is enough for to optimize over to produce a trajectory dependent policy that solves the problems that we want. So instead of paying this size of all possible trajectory dependent policies, we can pay the size of only this quantity, which is, again, just the set of potential optimal policies over these problems, if we restrict our search to this set. Now here, and I don't think I...
Sorry, can I ask you a question?
Yeah.
So does this mean that there will be some policy in the whole policy set that is not optimal for any policy and any of the problem? I see.
Right. Yeah, exactly.
That's
so
interesting.
this is a subset of this, right? And in some sense, basically, like if you can cover, then the next thing is just sort of saying that if you can, so you need to measure the size of this set in some way, right? So how it ends up showing up in the bounds is you need some kind of metric to measure the size of the space and compute an epsilon cover of this set. So it's just a way of measuring how large this set of optimal policies is.
It is because you're fixing a function phi, and if you allow phi to change, then you should cover all the possible policies.
Oh,
right?
yeah, correct. Yeah, correct. Phi is fixed, like it's given by, that's why it's here, right? It's like given phi, how many problems can there be? And of course, this is also like with an S and A here. So like the size of S, the size of A. Okay, so but that was a great question. So basically then what we need to come up with is a way to get a epsilon cover a representative set of these policies for the bounds to hold. And what you can then show is that like an epsilon cover of each one of these elements, so the initial state distribution, the dynamics distribution, and like the space of dynamics, and then the reward model is enough to basically give you, so if you get optimal policies for elements in this epsilon cover of all these triplets, then they basically cover also the policy space, the value function space. Okay, so I mean, maybe that was a little bit technical, but all there is here is that there's a lot of history-dependent policies that is super exponential, so that's not good for us. But in fact, in our problems, not all of these policies are actually optimal. So really, our optimization can be run over the set of only the set of optimal policies for problems of the type that we are trying to solve. And that set of policies has a statistical complexity that is polynomial in the size of S, A, H, and D. Okay.
Maybe one question, Aldo. So this result is like an existence, or you have also a constructive method for creating this covering?
No, this is right. So this is more like we assume you can get it. Okay, so what I'll show you is that this is for general phis. This is like you assume you can compute this set of like pi phi. And so it's kind of an oracle, completely inefficient. It computationally inefficient, statistically efficient, but computationally inefficient. I'll show you later on that under some assumption of phi, you can get an algorithm that is in the tabular setting tractable.
Okay, good. Thank you.
Yeah, perfect. Cool. I'm happy everyone is asking questions. So then the next thing is, so how does the algorithm work? The algorithm has to compute different uncertainty values. So for example, model uncertainty on the dynamics. So this is the usual notation that exists in reinforcement learning papers that corresponds to the number of times action A was played at state S in the data set so far up to time t. So how many times have we landed on state S and played action A? So this is just a number, but it'll appear later on in the uncertainty quantification that we have. So let me, because maybe this is kind of too technical, but yeah, okay. So how the algorithm will work is we will compute these surrogate trajectory reward values that correspond of two terms. The first term is the reward uncertainty given by the reward model. So how this works is, and we'll evaluate it at W hat t. But okay, so but given a model for the reward that we will compute its uncertainty by computing this quantity. So this is just mu of this reward model evaluated at this phi, plus the covariance of the features we have seen so far, plus the current feature of this trajectory evaluated in the inverse covariance of the features seen so far. This is some form of this 1 over root nt, or number of times you have seen a particular dimension of this phi feature, but done in a covariance sort of way. So anyway, so just the takeaway here, there's too much math, but really what's happening is that we have to define this kind of optimistic trajectory reward estimators that consist of two terms. One is an optimistic reward estimator given, and the optimism here is over reward models. And then the second term is optimistic reward estimator, which is more like a model uncertainty kind of correction term that ensures we are going to be optimistic, but also not only with respect to our uncertainty on the reward model, but also with respect to our uncertainty on the dynamics. Okay, wait, what did I do? I think I clicked the wrong thing. And so this is the main theorem we're going to be able to show. So this is just saying that the regret can be upper bounded by, right. So this quantity is polynomial in H, S, A. So the H dependence is probably not optimal. We don't use in this work like variance kind of tricks to make the H dependence better, and also the S dependence could probably be reduced. I think the A dependence is optimal, but this is using the general template of UCBBI, where you compute the empirical model, run policies, or compute an optimal policy to run in the empirical model using the bonuses I mentioned before. And this result is obtained with high probability. Yeah, so really, the important thing is the dependence on the model, or the parameters of the MDP is polynomial. And here again is the kappa value. So the kappa value, as I mentioned, if the reward model is very picky, very hard to learn, this will become very large. And the reward model could be very hard to learn if the W star parameter has a very large norm, because that means that the feedback you're going to get is either 0, 1, but very strongly 0 or strongly 1 in a sense. So there's not that much noise there. And as I kept saying, that the main analysis challenges are that the model is not known, and and because of the model that we are, the reward model is not known, sorry, and because of the nonlinearity, the signal is non-Markovian, so the optimal policy is history dependent. So the proof components is, as you would expect, is so it's as follows. So first we define an approximate value function, which is this quantity v tilde t pi, that is in the empirical model, so the model that we can build so far with the transitions we have observed so far, of the optimistic reward model I mentioned before. Again, the optimistic reward model has a component that is trying to be optimistic with respect to the knowledge of the reward parameter, W star, and then another component that corresponds to uncertainty about the model. So those are two necessary things. And then just so I can go through a little bit of the proof sketch, we'll use the following notation to ease notation, the notational burden, which is v tilde t will correspond to the v tilde, so this quantity, the optimistic value function of the pi t policy, the policy we played at time t, and this is the notation we'll use for pi star. Okay, so just because somehow it was not there probably written, but the algorithm, what it does is it computes these quantities using value iteration in the model for all policies. Okay, or let's say it does it in some other way in the computation efficient algorithm, and then we play the policy that maximizes this quantity. So that's the algorithm. The algorithm computes these values in the empirical model for all policies, and then the policies that I mentioned before, the pi phi policies, the all plausible optimal policies, and then just picks the policy in that set that maximizes this optimistic value function. Okay, and so the first thing is why this is called optimistic or optimism is that for all time steps, you have that v star is always upper bounded by v tilde t. So by v tilde t star. So the optimistic version in the model of the value function of v star. And now because by definition, we have that v tilde t, so the optimistic value function of the policy we actually chose is also bigger than the optimistic value function of pi star, then this is also always upper bounded by vt, which somehow I didn't write there, but that's also true. So basically, the following three, actually, this probably should have just been without the star here. That would have been better. So what happens is v star is always less than v tilde t without the star here. And the following things also happen. So we have that I don't think I defined these other things, but basically what you can show is that the v tilde t's minus vt's, so this one here, oh my god. So this quantity minus this one is also upper bounded by a sum of bonuses in the model and reward bonuses. So this intermediate v hat here is a value function where in the true model, where the optimism only comes from the uncertainty on the reward model. Okay. And one thing that is a little bit different here than the usual RL proofs is that here we require a path-dependent simulation lemma because of the policies being history dependent. Okay, so this is roughly the very, very high level view of how you prove something like this. So this is the usual sort of approach, but adapted, of course, to this history dependent and non-Markovian kind of feedback. And I'll just tell you maybe from a high level what happens when in a setting where you can find a computationally efficient kind of algorithm. So in the setting of the features being sum decomposable, which corresponds to this situation, yeah, so we can get a computationally efficient algorithm, and roughly what's happening is that the history-dependent policy that is optimal in this case only needs to know what is the partial sum of W star times these features. And because of that, the history-dependent kind of policy class that we are playing with will be much smaller, or actually identifiable. Basically, it's like policies that have taken into account the previous state plus the partial sum of the 5 features of states before times W star. Since W star is not known, that needs to kind of be learned. And in some way,
And maybe one question. So how large is this policy class actually? So you say it's kind of tractable, but it seems like you need to enlarge the state by something which kind of counts all your information.
Yeah, so here
this is quite large, no?
How I didn't. Right, no. So yeah, so here I didn't write it very well, but so the actual so think of it as taking the original state space and cross product or times, let's say 0, 1, the interval 0, 1. That would be kind of enough for capturing this kind of the space of optimal policies when the features are sum decomposable. That is because so in this setting, all you need to know from the past, let's say you are time h plus 1. Okay, so all you need to know from the features up to time h, if you know W star, let's say you know W star, all you need to know is the dot product between W star and the sum of the features before you. So if you know that, then, and you're in a particular state now, that's all you needed to know about the past. So in some sense, what happened is you can summarize the past into something small.
So you would not need to know, for example, this auto product of phi's, because this would intuitively tell me that you would need this as well.
The outer, no, you need to, yeah, that will be also useful in that's useful, of course, in the estimation of the optimistic rewards and all these things. But all I'm trying to say is that in the case of some decomposable features, the space of history-dependent policies that matters is actually this space, the set of policies that compute the partial sums of phi's times W star from the previous state you have visited, and in a sense appends that sum to your current state. So provided you know that sum of partial dot products, you don't need to know what exactly happened in terms of the actual states that you visited before.
Okay, yeah, well, okay.
Yeah, so that
I find it very counterintuitive, because I would say that you would also need to do some kind of exploration, and in order to have that, you need to know what you explored before. And if you just project everything on W, then you don't know what you export in the previous rounds. So this is what I'm
exploration.
confused.
Oh, no. So exploration is still there. I mean, all of the issues of exploration are still there. The thing that is perhaps easier to think about first is the what's the name? This thing that the space of history-dependent policies is something that you can actually compute in a efficient sort of way. So previously there was this set of policies that were optimal for like problems in this class. So that set is like very hard to compute in general for a phi, an arbitrary phi. But for this set of phi's, the set of optimal policies is actually kind of a simple set. It's a set that would take into account just the dot products of the history with with W star, and just record that scalar and keep that and sort of in a sense append that to the current state. You still have issues of exploration and issues like surrounding all of that, but the space of policies that are history dependent here for this kind of problem where the features are some decomposable becomes something you can actually operate with.
Yeah, I know. I think I understand. Yeah.
Yeah. Maybe I should have said, but
So, so the optimal policy really just depends on this.
yes.
And
Exactly,
you can
exactly.
search within this class, you say, which are parameterized as the
Right.
optimal policy. You don't need to kind of enlarge it to
Right.
take it.
Yeah.
got it.
So before it was just some sort of abstract, I mean, something that exists, but computing it is very hard in general for general phi maps. But for this specific some decomposable thing, there's an easy way to decompose, to basically write down that set of policies, and that set of policies is like small. I mean, it's bigger than the Markovian set of policies, but it's not that big.
Yeah.
And one thing I want to sort of, I guess, emphasize here is that something interesting happened here, because the algorithm in some way what ends up doing is learning this way of summarizing partial trajectories. So what this algorithm will sort of boil down to is you have the W hat rework model that can allow you to like compute these partial sums and then use on top of these partial sums of like values the search over this set of policies. So what happened here is somehow you learn the way of summarizing the history. Given that you have this function class that produces, over which you are searching, that produces these summaries. So I'll come back in like a future work section to that. So, I mean, again, for this kind of approach, you can also get some regret guarantees that look similar to what I mentioned. We also assume some other things to make it tractable, really, or to make this thing doable, which is that there's always some policy that for each kind of feature, like for each H, horizon level H, can produce a covariance matrix that has a minimum eigenvalue. So that one is some kind of, there's always an exploration policy you can find, you don't know it in advance, that has a minimum eigenvalue. And that becomes useful in some part of the result. And of course, it appears here in the guarantees. So I'll just move a little bit to the next one, but I don't have too many slides here. So maybe I'll pause for a second. Like if there's some more questions, please let me know.
I'm just curious about the regret guarantee on the previous slide. It seems that you get n to the power of 2/3, right?
Yeah.
So where does this additional
in
comparison to the previous one? Where do you lose a factor?
Right. So this is because in this algorithm, we need to make use of this assumption that there is a policy that produces a covariance matrix that has a minimum eigenvalue for all little h things. So ultimately, what ends up happening is you get some form of epsilon greedy thing going on.
I see.
And that's what I mean.
And that's sufficient for enough of exploration, sort of.
Yeah. So right. So we have to modify the previous algorithm for this to work out. But there are two things that make this tractable. One is the policy class becomes tractable. And then the second one is that we require this minimum eigenvalue assumption. So I guess perhaps an open thing if the minimum eigenvalue assumption is required or not really for this to work out in practice, I guess, but for these results to hold.
I see.
For some
Thanks.
Okay, so for this work is joint work with Adirupa, who's now at Apple, and Jonathan. So she was at Microsoft before. Jonathan Lee at Stanford. And me. Okay. So what we so I didn't delete this one, but what we assume here instead of so in the previous one, what we saw is a model where the feedback comes by evaluating trajectories as good or bad. Now here we think of the setting of dueling feedback, where first the assumption is that you have a way of evaluating pairs of trajectories, and the model is the same, so but for pairs. So the model is that we have a feature map that embeds trajectories, and you can evaluate how better a trajectory is with respect to another one by, this is the probability distribution evaluated at this nonlinearity here. So this leads to a comparison between policies, which we assume using the same kind of model. And then the regret that we are hoping to minimize is this kind of quantity. So now notice that the mu part disappeared. And so we are just comparing the sort of reward part, which is just the linear part inside the mu. So you can relate. So you may ask here, oh, so this doesn't look like these other quantities here, the mu convolved linear parts. You can sort of relate this part with a version that instead looks like max over pi, and then probability of pi with respect to mu1 here, plus the probability of pi star greater than mu2. So you can sort of relate these two up to some kind of linear factor that corresponds to, again, the peakiness of the mu function. And then, I mean, all I wanted to say really is that we can also get similar kind of guarantees in this setting. So the main challenge is that the feedback is given by this, but the evaluation is at the sort of population level instead. So converting this kind of feedback that allows you to learn the reward model into something that works for this kind of evaluation, that is how you evaluate how two policies compare to each other, is a little bit well, it's sort of a technical challenge. Now, one thing is like, why this evaluation this way versus doing something else, is because so extending this kind of per trajectory feedback model to evaluating policies is a little bit, I mean, you could do it in many ways, but we chose this because it felt the more sort of natural in a sense to assume here. Another thing one could do is to sort of take two policies and say that their evaluation is taking arbitrary pairs of trajectories from these two policies and comparing them according to this mu model. But that felt a little bit suboptimal. So we ended up choosing this instead, which eventually basically gives rise to this kind of objective that is a little bit like, it's an expectation objective of the 5 features. So also, maybe I didn't mention, but phi of a policy is the expected phi map of a given policy. So that's the expected phi of the trajectory sampled from a particular policy. Okay, so this work is going to appear at AI Stats this year. So, and it's also online, so you can take a look at the details there if you're interested. And then just, I guess, a couple of future directions because we are running out of time. So more, I guess, thinking of more computationally kind of efficient algorithms that have root and regret. We showed one with n to the 2/3 regret, but there could be potentially computationally efficient versions that have root and regret. And then I mentioned that in the sum decomposable case, roughly what's happening is that in that setting, you're kind of learning over POMDPs, where you have a learnable state component that is a scalar in this case, like the sum of the features so far times W star. So there could be a nice little theory sort of project here of thinking about learning POMDPs with a learnable state component, where the hidden state is something you can learn from data, and what kind of algorithms can you give for that. There may exist some work that cannot do this already, and people that may be doing something like that, but it's an interesting project. The other thing is, of course, So some of these algorithms that I showed you are, in the tabular settings, so are very expensive. And in the paper, we have some simple experiments that use policy gradients to optimize over trajectory feedback. So perhaps getting guarantees for policy gradients, theoretical guarantees, when you have once per episode feedback and characterize how hard that is, would be also very interesting. And then another super interesting thing would be when you think about using a reward model, learning a reward model to then make use of that reward model to give once per episode feedback to an algorithm. An interesting sort of thing one could do is to use an active learning algorithm to learn a good reward model, so that can be used downstream to train like a once per episode sort of good policy. And so understanding those trade-offs would also be, I think, of great interest. And that's it. Somehow I have yep. Yeah, so any questions, last comments, questions, let me know. But I guess we are at 1 hour, so.
I have a quick question, if I may go. So you have this setting of some decomposable features, right? Where doesn't it somehow again enforce Markovianity? Like, doesn't it enforce Markovian structure back to the problem, where your reward structure is kind of additive rather than being like non-additive rewards?
Well, it's not completely Markovian, right? Because the reward also goes through the nonlinearity at the end. So the nonlinearity does some kind of product of all these. So think of it as maybe like you had just rewards, Markovian rewards, and then you pass it through a nonlinearity at the end. So nonlinearity will multiply the different rewards at the different time steps and like make it basically non-Markovian. What does happen is that there is a way to add something to the state space, like this sort of scalar that you can learn, that can then make the problem Markovian, but that's something that you have to learn from data. So it's like you can turn the problem Markovian by learning from data the Markovian, like something you can basically the PondVP, the hidden state.
Okay.
If that makes sense.
Yeah.
Any other questions? Maybe what we always do, we always turn off the recording and then ask the controversial questions. So I think now is a good time to turn off.